Yeah, actually for today's courses, it should be Pak Miki deliver the courses, but Pak Miki have another commitments, yeah, that he need to do for today. So I will try to fill in, yeah, the course for today. So we will continue. It's still in the chapter 3, yeah, from Pak Heri's book, yeah, is regarding boiler, yeah. So in the last meeting on, when is our last meeting is on Wednesday, yesterday, yeah. So yesterday we have already learned regarding the energy balance of boilers, yeah, and we have already learned also the boiler flue gas, as well as we learned regarding the boiler efficiency and also the heat losses, yeah. So the major heat losses from the boilers, yeah, that is actually commonly considered in order to define the boiler efficiency, yeah. Okay, so for today, we will actually learn regarding the problems, yeah, several problems examples, especially in evaluating the boiler efficiency, yeah. Okay, I will share the slide first. Okay, so hopefully the slide is already appeared in your screen. Yeah, so yeah, we will do some or try to solve several problems. Yeah, in evaluating the boiler efficiency. Yeah. Okay, the first problem examples is yeah, this one. Yeah, so where we have the a boiler which is operated with oil as a fuel. So we have the C10, yeah, which is actually the octane, yeah, with the lower heating values of 33,800 kilojoule per kilogram, yeah. And at boiler testing, the compositions of the flue gas, yeah, in the dry basis is actually 30%, yeah, more CO2, and have also 1% more CO, 7% small oxygens, and the rest is nitrogens, which is 79%. Yeah. And we have the temperature of the flue gas is 280 degrees C, and we need to estimate the boiler thermal efficiency, yeah, where we use the temperature reference is 25 degrees C. Yeah. And we assumes, yeah, several losses, yeah, in here. So consider the UCL. Anyone still remember what is the UCL? What is UCL? What is MCAL? What
UCL is the uncombusted carbon loss.
Okay, uncombusted carbon loss. Yeah, so it's actually the loss which is actually due to the carbon from the fuel, which is not actually combusted. Yeah. So we assumes that the UCL values is equals to 0. Yeah. And we have also MCAL. What is MCAL? Anyone still remember?
MCAL is the moisture combustion air loss.
Okay, moistures in combustions air loss. Yeah. So we ignore also, yeah, the contributions of the MCAL in this case. So we define it as, or we assume it as a 0. And we have also the RUL. So RUL is the radiations and unaccounted for losses. Yeah. So it's actually the losses except the other 5 losses. Yeah. So we have the DGL. We have also ML. Yeah. Dry gas losses. We have also moisture losses. Yeah. And also we have ICL, which is incomplete combustion losses. Yeah. So the RUL is the other losses except the other 5 major losses. Yeah. Okay, so in this case, the heat capacity of the gases is already given. Yeah, so we have the heat capacity of the carbon dioxide is 53.5 joule per mole degree C. Yeah, we have also the heat capacity of the CO, water, oxygens, and nitrogens. Yeah. And the illustrations or the schematic on the right-hand side is illustrated the MFO burning. So the MFO is the, we define it as the medium fuel oil burning, yeah, and which is actually a type of the skid mounted, yeah, with the capacity of the 5 ton per hours, yeah, package boiler. So we have also another type of the boilers. We call it the trailer mounted. Yeah. So we have a skid mounted and we have also the trailer mounted. Yeah. So you can have a look later on. Maybe yeah, try to search it. What is actually the main difference between these two type of the boiler? Yeah. And you can actually have a look yeah from the website and also from other reference. Yeah. What is the advantages and disadvantages for this type of the boilers? Okay, so we try to solve these problems. Yeah. So the first thing we need to do is we need to define the fuel compositions. Yeah, first. Okay, by using yeah, we try to calculate it first the C and H compositions. Yeah, the carbon and also hydrogens. So either or both in the mole percent mole basis and also percent mass basis. Yeah. So in percent mole basis, we can actually have a look here because we have C10, which is actually octane. Yeah. Oh, sorry, C10H22. Yeah. So if we want to find the fuel compositions of, for example, of C and H, yeah, based on this fuels, yeah, C10H22, we can just have a look through the amount, yeah, amount of the carbon, also amount of the hydrogens. Yeah. So to calculate the mole basis of the carbon, we can just divide it the amount of the carbon and also the hydrogens. Yeah. So for the carbon, we have yeah, this one is actually the amount of the carbon divided by the total amount of the carbon and hydrogens. Yeah. Sorry, my pen is not working on the left hand side of my screen. Yeah. So this one, yeah. So 10 divided by the 10 plus 22. So multiplied by 100%, then we have around 31.25% more. And the rest of the and the rest is actually the hydrogens. Yeah. So the hydrogens is 100% minus 31.25% more. So we have 68.75% more. Okay, so if we would like to find the percent mass, yeah, of carbon and hydrogens, we can just multiply the amount of the carbon and hydrogens with the atomic relative mass, yeah, of its corresponding fuel. Yeah. So for the carbon, we multiply with 12 as a relative atomic mass, yeah, 10 times 12. While for the hydrogens we have 1 gram per mole. Yeah. So for the atomic mass relative of the hydrogen is 1. Yeah. So we can just calculate it. Yeah. And after that we can get the percent mass of carbon and also the hydrogens. Yeah, which is 84.5% mass and 15.5% mass respectively. Okay, so the second stage or the second step of solving these problems is we have to calculate the amount of the flue gas. Yeah, so we assumes the basis for 1 kilogram of fuels. Yeah, so we use the equations 3.10. Yeah? So I think Pamiki have already defined it in the previous slide. 3.10, yeah, that must be here. Yeah, so where the mass of the flue gas per mass of fuel is equals to the conversion factor depending on the type of fuel used. Yeah, so divided as the C multiplied by this. Yeah, so 44 is actually the relative molecular mass of the carbon dioxide. We have 32 here. Yeah, so the relative mass molecule of the oxygens, 28, yeah, as a relative mass molecule of the CO and nitrogens, and we have also yeah, divided by the 12. Yeah, so the 12 in here is actually the atomic mass relative of the carbon. Okay, times multiplied by CO2 and CO. Okay, because we have two carbon sources in here. Yeah, is coming from the CO2 and CO. So that's why we consider these two molecules, yeah, as carbon sources. Okay, so we go back to here. Yeah, so we can just put, yeah, the each parameters. Yeah, in here we have the constant, so we get 0.845 is actually from this. Yeah, so this is from the percent mass of the carbons, yeah, based on the fuel compositions calculation. Yeah, so we have 0.845, and we can just we can just put all of the numbers given from the questions. Yeah, so we have 0.13 for CO, 0.13 for CO2, 0.01 for CO, 0.07 for oxygens, and 0.79 for nitrogens. Yeah, so we put it here. Yeah, and yeah, this one we merge it. Yeah, why we merge it? Because the nitrogens and also CO have the same molecular weight. Yeah. Molecular, so the molecular weight of these two is actually 20 gram per mole. This one also the same. So that's why we merge it together in order to make it easier. Okay, so divided by 12 times CO plus CO2, yeah, which is 0.19 and 0.01. And we will have the amount of the flue gas is 15.27, yeah, kilogram per kilogram fuels. Okay, so move on to the next one. So we have to calculate the loss. Yeah. So the first one, we have to calculate the dry gas loss. Yeah, which is actually the DGL. We have to calculate also the moisture loss. Yeah, we have to calculate the incomplete combustion loss, and we have to calculate the RUL. Okay, so before that, we have to also calculate the BM. Yeah? So the BM in here abbreviated to the molecular weight of the flue gas. So it depends, or it is actually as a functions of the percentage, yeah, of the flue gas given from the problems. So we multiply the molecular weight of each compounds, yeah, multiply by the percentage, or the mole fractions of each components. Yeah. So in here we have based on the problems, yeah, we have 13% for CO2, 1% for CO, 7% for oxygens, and 79% of the nitrogens. So we calculate the molecular weight. So this one is the molecular weight of the flue gas. Yeah. Of flue gas. So it's actually based on, again, the percentage of the each compositions multiplied by the molecular weight of each compound. So this one is for CO2. Yeah, this is for the 1% is for the CO. Yeah, 7% for the oxygens. So this is oxygens. This is CO. This is CO2. Yeah, and this is for the nitrogens. Okay, so we will get these values here, 13.36 gram per moles. And then we calculated the CP, or the heat capacity of the flue gas. Again, this is actually the same way with the previous one to define the kind of the molecular weight of the flue gas. Yeah, so we multiply the heat capacity, divide it from the problems, of the gases, of each gases, multiply by the percentage. Yeah, so this given values, multiplied by the percentage of each compounds. Okay. Okay, so we will have the CP of the flue gas, which is 35.55 joule per mole Kelvin. And then we calculate the dry gas losses. Yeah, so the DGL, we have actually the formula of the DGL is equals to mass of the flue gas, yeah, multiplied by the Cp of the flue gas, yeah, multiplied by the temperature of the flue gas minus temperature of the reference. Okay, so we have the mass of the flue gas in here, which is 15.27. And we have also the Cp of the flue gas, yeah. So the Cp of the flue gas is actually, we need to correct it, yeah, with the molecular weight. So that's why in here we calculate it based on this formula, yeah, Cpfg divided by the Bm, yeah. So 35.55 divided by 30.36. Okay, sorry if we use the comma, yeah, as the decimal separator. So we should use dots instead of comma. So sorry for the inconvenience. And we have also the temperature here, yeah. So based on the problems, we have the temperature of the flue gas is 280 degrees C, and we have the temperature reference is 25 degrees C. Okay, so we can just put it the numbers in here, and we get the dry gas losses, which is 4,559 kilojoule per kilogram fuels. Yeah. And then we calculate the next losses, which is moisture losses. Yeah. So the moisture losses is the formula to calculate the moisture losses is 30. Sorry. What is the formula? So the Cp, is it correct? The Cp. Wait, 37.6 divided by 18. So this is the same, yeah. So we have the temperature of the flue gas minus the difference between the temperature of the flue gas minus the temperatures of the reference, and we have the, what is 37.6 in here? Let me have a look at the formula first. Yeah. Okay, so we have the moisture losses, which is 0.46. Just in BTU. So we have actually the formula is given in here. Yeah, so we have the Cp of the water and multiplied by the 9 times the H, yeah, and plus W, and multiplied by the difference between the temperature of the flue gas minus temperature of the reference. Yeah. So we have a Cp 9H plus W multiplied by the T flue gas minus the ref. Okay, so what is the H values in here? How do we get 0.155? Let me have a look. Okay, from here, yeah. So we have the mass of the percent mass of the hydrogens, yeah, which is 0.155. Yeah, so we put it over here. Yeah. While for the W, so the W is actually corresponding to the let me have a look at first. Okay, we assume that the W in here is actually equals to 0. Yeah. And we multiply by the Cp, yeah, Cp of the water. So we have 37.6. Yeah. It's actually from, let me have a look here. So we have the Cp of the water, yeah, 37.6 joule per mole degree C. So we divide it by the molecular weight of the water, yeah, which is actually 18, yeah, and multiply by the difference between the temperature of the flue gas and temperature of the reference. Okay, so we will have the moisture losses of 743.1 kilojoule per kilogram fuels. Yeah. Okay, next we go to the ICL. Yeah, so incomplete combustion losses.
Sir, sorry, sir. I want to ask, sir.
Yeah, go
In
ahead.
the formula before, why is it 0.46, sir? I still don't understand, sir.
Okay, so this one, yeah, so 0.46 is actually Cp of the water vapor in BTU L per pounds, yeah, of the water vapor in degree Fahrenheit. Yeah. So it's actually, it depends on the problems, yeah. So this is actually the units, yeah, for the 0.46 is actually the units. We have BTU per LB, yeah. If we put it in the different units, so we will have another unit is kilojoule per kilomole Kelvin. Yeah. So I think this is BTU LB degree Fahrenheit. Yeah. So we have 33.57. Yeah. But if in the problems, yeah, in the questions is actually the Cp is given, yeah, in the problems. So in here we have the Cp, yeah, of the water, yeah, the heat capacity of the water vapor is 37.6. Then we need to use this one. Yeah, just use the given parameters from the problems. Otherwise, if it's actually not given, then we can use the CP yeah, the CP reference, yeah, given from the formula. Whether is, yeah, it depends also on the units, yeah. Is it clear, Kevin?
Yes, sir. So if the unit is kilojoule per kilomole, just use the Cp of water divided by the MR of water, right, sir?
Yeah, correct.
Okay. Thank you, sir.
Yeah. Okay, yeah. So we go ahead with the next losses, yeah, which is the ICL. Yeah. So we calculated the incomplete combustion losses, where the formula is actually given, yeah, in the here. I think you already give you ICL. Yeah, this one. Yeah. So we have the mass of the flue gas multiplied by the 28 times CO, 44 divided by the 44 times CO2, 28 times CO plus 28 times nitrogens and 32 times oxygens multiplied by 4,380, where this values is attributed to the heat of the combustions, yeah, of the CO in BTU per pound. Yeah. Okay, so in here, so we can actually calculate it, yeah, for the incomplete combustion losses. So we have the mass of the flue gas is 15.27, yeah, and we have also the yeah, this one, yeah, the percentage of each compounds, yeah. So it's actually given from the questions, yeah. And we have also 4,380. Let me have a look first, yeah, because we should use the other formula, or we should use the other units, yeah, instead of 4,380. I think there is a mistake, yeah, in here. If we want to use the units of the kilojoule per kilogram, then we need to change these values, yeah? Because as mentioned from here that the 4,380 is actually in BTU per pound. Okay, so let me check it first. For the values in kilojoule per kilogram, it must be 10,178. Yeah, sorry, yeah, there is actually a mistake in here. Okay, so it should be the ICL losses is 1,430.5. Yeah. Okay, again, be careful, yeah, in evaluating the losses. Yeah, so you have to be careful, especially to the units. Yeah, so if the units in BTU per pound, then you use these values, yeah, as the heat of the combustions of the carbon monoxide. Yeah. While if the units in kilojoule per kilogram, then we have to use this. Yeah, 10,178 kilojoule per kilogram. Okay, so the last one, we have to calculate the RUL. Yeah, so the RULs based on the, or RUL, we divide it as the radiations and unaccounted for losses. Yeah. Based on the problems, it is stated that the RUL equals to 30% of input energy. Okay. Then we can use, yeah, the RULs is actually equals to this 3% of the input energy. Yeah. So 3% times the mass and also multiply by the LHV, yeah, or the lower heating values that is actually given from the problems. Yeah, so we have 33,800 kilojoule per kilogram. Okay, so we will get these values, 1,414 kilojoule per kilogram fuel. Then we have the total heat losses. Yeah, total heat losses just some summations of all of the losses. Yeah, so from BGL, from ML, yeah, sorry, from BGL, from ML, from ICL and RUL. Because we, from the problems, the UCL and MCAL, we assume it as a 0. So there is no contributions, yeah, from the uncombusted carbon losses, yeah, and also from the MCAL, yeah, which is actually the moistures in combustions air losses. Okay, so we need to revise it, yeah, because we have the ICL is slightly different. It's not slightly, it's significantly different. Yeah, it's around 4 times, I guess, 1,430.5. Yeah. Okay, so you can calculate it. Yeah, so I'll try to calculate it as well. Plus 743.1 plus 1,430.5 plus 1,040. Then we have 7,746.6. Okay, this one. Then we will have 7,746.6. Yeah. Okay. I think it should be in the absolute values, yeah, in here, right? Because if it's not in absolute values, then the results will be negative. Yeah. No, it's 33,000. Yeah? Oh, sorry. I thought it's 3,000. Okay, 33,800 minus 7 minus 7.6.6 divided by 77%. Yeah? So it's slightly reduced, yeah, because we have the losses, yeah, is actually increases, yeah, when we use the proper units of the combustion heat of the CO, yeah, for the incomplete combustion losses. So we have 77.1%. Okay, any questions for this problem? Okay, so if there is no questions, I will continue, yeah, with other problem example. Yeah, so we have the another problems is actually based on, yeah, we can actually get the data from the nomogram. Yeah, so this is actually one of the example of the nomogram of the oil fire boilers. Yeah, figure 3.2. Okay, so the dry gas losses commonly attributed as the largest heat loss component, yeah, compared with other losses, yeah, the DGL. And the performance of the boilers is commonly stated as the correlations between the boiler efficiency, yeah, and also with oxygens and carbon dioxide concentrations. Yeah, and the flue gas temperature as well. Okay, and the oxygen concentrations in flue gas indicates the excess of the air, yeah, in the system. Yeah, and one example of the energy and mass balance calculations in combustions is given in the form of nomograph, yeah, as stated in figure 3.2. Okay, so for examples, we have the measurements of the flue gas, yeah, which actually gives the parameters which is given is actually temperature and oxygen concentrations in flue gas. Yeah, so we have this nomograph here. So it looks like two graphic which is actually merged together. Yeah, so the below graphic is just the percentage of the oxygens, and the above graphic, yeah, here is actually the graphic between the total flue gas losses versus carbon dioxide, yeah, percentage or concentrations. Okay, so we have the temperature of 225 degrees C, yeah, and also, yeah, this is actually as a functions of the temperature of the flue gases, yeah, this line, yeah. So we have several temperature from 150 until 350 degrees C, yeah. So because commonly the exit gas temperature from the flue gas, yeah, maximum, yeah, is in the range of this temperature. Okay. So for example, we have temperature of the flue gas 225, yeah, so which is actually this line. And we have the oxygen concentrations in flue gas is 7.8%. Yeah. Okay, so we have this. Choose one. Okay, 7.8% is actually around here. Okay? So we need to determine the CO2 concentrations as well as the heat loss with the flue gas, yeah, or the total flue gas losses. Okay, so based on this, so we can just interpolate the lines, yeah. So we just take the straight line horizontally, yeah, to the right hand side until it intersected with this line, yeah, this curve. So, and then after that, we just take the straight line vertically, yeah, here, until it's actually intersected with the desired temperature, yeah, or the known temperature of the flue gases, which is 225 degrees C, yeah. And then we will get the total flue gas losses, yeah. Yeah, just yeah, interpolating the line to the left hand side vertically, horizontally, yeah, until it intersected with the y-axis. Yeah, so we will have the heat loss with the flue gases is 18%. Yeah, while the CO2 concentrations, we can see it here from here. So this line is intersected also the x-axis. Yeah, so this is actually the concentrations of the carbon dioxide in the flue gases, yeah, which is 9.8%, yeah, stated in this slide. Okay, so this is actually the way how we can actually estimate, yeah, the heat losses, total flue gas losses, yeah, based on the nomograph. Yeah, so at least we have to get the informations of two parameters, yeah, either is temperature or oxygen concentrations or CO2 concentrations, yeah, in order to get the informations of the heat loss with the flue gas. Okay, any questions for this type of the problems?
Sir.
Yep.
For the heat loss with flue gas, why is it HHV basis or not LHV, sir?
It's a good question. Yeah. So for the heat losses, why it is actually HHV basis? Yeah. So this is actually, as far as I know, this is actually the rule of thumbs, yeah, of the heat losses based on this nomograph of type of the nomograph, yeah. So the percentage divided as the y-axis in here, yeah. So this is actually already stated, yeah, as a GCV, yeah. So the GCV is actually gross calorific values, which is actually similar with the HHV basis. Yeah. So this is just already divided, yeah, based on this nomograph. So there is no exact reasons why there is actually HHV basis, yeah, but it is actually already plotted, yeah, based on the authors, yeah, of this nomograph. Hope is answering your questions, Kevin.
Yes, sir. Thank you, sir.
Okay, so if there is no more questions, we can continue, yeah, with other problems, example, yeah. Okay, wait, take a drink first, yeah. Sorry. Okay. So the next example is yeah, regarding the steel in boiler, yeah. So we have the boiler which is operated using the oil fuel, yeah, which only consists of the carbon and hydrogens. Yeah. Okay, so the HHV of this fuel is 43.52 megajoule per kilograms. Yeah. And we have the air in the dry gases, yeah, or in the dry conditions, and oil enter the furnace at temperature of 25 degrees C, while the exit flue gas temperature is 300 degrees C. And the flue gas compositions consist of this, yeah, in the dry gases, we have 11.2% of the carbon dioxide, 0.4% of the carbon monoxide, and we have 6.2% of the oxygens, while the rest is nitrogens, 82.2% of the nitrogens. So we need to determine the combustion's efficiency again, yeah, in the furnace. Okay, so the informations given also in this problem is the heat capacity, yeah, for each gases, CO2, CO, water vapor, and also oxygens and nitrogens. Okay, so the first thing we need to do is we need to define first the basis. Yeah? So the basis of the dry flue gas, we define it as 100 moles. Okay, so we can actually calculate the mole of each components, yeah, based on the percentage given from the problems, yeah, where the CO2 is 11.2%, yeah, so just 11.2% multiplied by 100, yeah, same with other gases, yeah, CO 0.4%, oxygen 6.2%, and nitrogen 82.2%. Okay, and the next step is we assumes that the amount of the incoming air can be calculated from the nitrogen balance, yeah, with the approach that nitrogens only comes from the air. Yeah. So we can calculate the mole of air first, yeah, by dividing the mole of the nitrogens given in here, which is 82.2 moles, yeah, divided by the percentage, yeah, divided of the percent compositions, yeah, in here, yeah, sorry. No. I mean, 79% we assume that this is actually the percentage of nitrogens in the atmosphere. Yeah. So we can define it. The mole of the air is 104.05 moles. Yeah. So we assume that in the atmosphere, we have the oxygens and nitrogens, yeah, with the percentage of the 79% of nitrogens and 21% of the oxygens. Okay, so after that, we calculate the mole of the oxygens from air. Yeah, so just multiplying this, yeah, 21% multiplied by the mole of the air, yeah, 104.05 moles. So we have 21.85 moles. And we need to calculate also the mole of the oxygens, which is actually react, yeah, to form the CO2. Yeah, so the carbon plus oxygens will give you the CO. Y is actually divided by 2 here. So we have actually the CO is 0.4 moles here. Okay, by using a stoichiometric here, in here. Y this is actually divided by 2 in here in order to get the mole of oxygens, which is reacted with the carbon in order to generate the CO. Anyone? Mole of the oxygen. So this is actually the one that we actually asked, the N oxygens, or the mole of the oxygens. Based on the stoichiometric approach, Y is actually divided by 2.
In the equation, there's the number of moles of O2 should be half.
Good, yeah. So this should be the coefficients of the oxygen should be half, yeah, in order to make it stoichiometric. Yeah. C plus half of the oxygens, yeah, and it will create CO. Yeah. Okay. So that's why in here we divide it by 2 in order to get the mole of the oxygens reacted, yeah, with the carbon to generate the carbon monoxide. Okay. And then we calculate also the mole of the oxygens, yeah, to react. This actually reacted to form the CO2. Yeah, so the C plus oxygens will create also CO2. Yeah, and the mole of the CO2 is given in here, 11.2 mole. Yeah, and yeah, the mole of oxygens will be equals to the mole of CO2. Yeah, because the coefficients of the oxygens is similar with the CO2. Yeah, so we have 11.2 moles. Okay, so and then the last one, not the last one, it's actually the next one is mole of the oxygens react to form the water. Yeah, so we can calculate it based on the mole of the oxygens input, yeah, minus mole of the oxygens which is actually reacted, yeah, and mole of the oxygens remaining. Okay, so the mole of the oxygen's input is actually coming from here. Yeah, so it's based on the calculations from basis of the air. Yeah, so we have 21.85 moles. Yeah, and we have 0.2 as the mole of the oxygen reacted. Yeah, to form the 0.2 minus, oh yeah, minus 0.2. So this is actually the moles which is actually reacted. Yeah. So to form the CO and CO2, we have 0.2 moles and 11.2 moles. Yeah. And we have the remaining oxygens. Yeah. So the remaining oxygens can be calculated from here. Yeah. So it's actually based on the mole of the each components. Yeah. We have 6.2 moles of the oxygens, yeah, based on the percentage, yeah, given from the problems, multiply with the basis, yeah, 100 moles. So we have 6.2 moles of the oxygens remaining. Okay, so we have the mole of the oxygens which is actually reacted to generate the water, which is 4.25 moles. Okay, so the next one is we need to calculate the mole of the water generated. Yeah, so based on these reactions where we have the 4H, yeah, or the 4 hydrogens plus oxygens will create the water. Yeah, then we can just calculate it based on the oxygens, this, yeah, this mole, yeah, multiplied by 2, yeah, because the coefficients in here we have 2 times higher compared with the oxygen, yeah, which is only 1. Okay, so we have 8.5 moles of the water generated. Yeah. Okay, so after that, we need to make the tabulations, yeah, in order to calculate the compositions of the wet flue gas. Yeah. In here, so we have the components, which is consists of the CO2, CO, oxygens, nitrogens, and water, with the corresponding moles, yeah, based on the percentage given in the problems, and we using a basis of 100 moles. Yeah. So we have these values, yeah, in moles, yeah, 11.2 moles, 0.4 mole, and so on, and the total is 108.5 moles. And if you want to make it in percentage, we can actually do the normalizations. Yeah, so we can just divide it 11.2 with total moles of the total mole of the compounds of the systems. Yeah. So in order to get the mole fractions, yeah, of each components. Yeah. So 11.2 divided by 108.5 times 100% to get the mole fractions of the CO2. Yeah. 0.4 divided by 108.5 times 100% to get the mole fractions of the CO and so on. Yeah. So for the oxygens, nitrogens, and water also do the same thing. Okay. The next one is still a long way to go. Okay, so the questions, I mean the problem is very short, but the answer is actually very long. Yeah. And after that, we need to after we calculate the mole of the oxygens, yeah, initials or the input of the mole oxygens, mole of the oxygens, which is actually reacted to generate several products, yeah, CO, CO2, and water, and also mole of the water generations, yeah. And we make also the compositions of the wet flue gas. After that, we calculate also the mole of the carbon in fuels, yeah, as well as the mole of the hydrogens in fuel. Okay, so we calculate from here. So the mole of the carbon in fuels is actually originated from the CO and CO2, yeah, as a carbon sources, yeah. So based on the problem, we have the 11.2 moles and 0.4 moles for CO2 and CO2, and for CO and CO2 respectively. Then we have 11.6 mole. Yeah. And we have mass of carbon in fuels as well. Yeah. So after we get 11.6 mole, so we can actually convert it to the gram, yeah, by multiplying with the atomic relative mass of the carbon. Yeah, so we have 139.2 grams. And we calculate also the mole of the hydrogen in fuels. Yeah, so we have 17 mole. Yeah, so in here we have yeah, by using the approach, yeah, using the water. So we have 2 mole of the hydrogens in water. Yeah. And multiply by 8.5 moles water, which is actually generated from here. Yeah, so the water generations here. And we calculated the mole of the hydrogens in fuels, yeah, by multiplying this, yeah, 2 mole of the hydrogens based on the from water, multiplied by 8.5 moles of the water. Yeah. So we have 17 moles, yeah, of the hydrogens in fuel. And if we convert it to grams, then we can just multiply by 1, yeah, gram per moles, then we have 17 grams. Yeah? Okay, that's why in here the mass of fuels, we can just do a summations of the carbon and hydrogens, the mass of the carbon and hydrogens, then we get 156.2 grams, yeah, or it's actually equals to 0.1562 kilograms. Okay, so after that, we calculate the input energy. Yeah, so we need to calculate the input energy based on these calculations. Yeah, so the input energy will be equals to the mass of fuels, yeah, multiplied by the HHP. Yeah, so mass of fuels we already get it, yeah, from the previous calculations, which is 0.1562 kilograms. We multiply by the HHP, yeah, then we get this, yeah, 6.798 megajoule. Okay, so it's not actually finished yet. So this is just the input energy. Yeah, so we need to, in order to calculate the efficiency, then we need to calculate again the heat losses. Yeah, so from dry gas losses, from moisture losses, yeah, incomplete combustion losses. Yeah, so we assume, yeah, in here I didn't actually put the assumptions. Yeah, so we need to assume that the losses consist of the DGL, ML, and ICL. Okay, so for the dry gas losses, so we can actually calculate it, yeah, based on the formula. So where the formula is actually the moles, yeah, of the species I multiplied by the heat capacity of the species I, yeah, multiplied by the difference between the temperature, yeah, the temperature of the exit flue gas and also the temperature of the reference. Okay, so I make the tabulations in order to make it easier. Yeah, so I put the, yeah, for each components, yeah, we have CO2, CO, oxygens, and nitrogens. Yeah, and we have the corresponding moles for each components. Yeah, 11.2, 0.4, 6.2, and 82.2. Yeah. And then we have also the heat capacity, which is actually given from the problems, yeah, for each component. And then we can just calculate it, the heat losses, yeah, for each component. And after that, we sum up all of this component in order to get the total heat losses based on the DGL, yeah, the dry gas losses. Don't forget to change it to megajoule, yeah, because yeah, we would like to make it the same with the input energy, yeah, and at the ends, yeah, in order to make it easier to calculate the boiler efficiency. Yeah. Okay, so once we calculate the dry gas losses, yeah, we can move on to the moisture losses, yeah, where the moisture losses also can be actually calculated using this formula, yeah. So the formula of calculating the moisture losses is mole of the, yeah, there's actually several ways, yeah, actually to calculate the moisture losses and dry gas losses, yeah. So previously we used for the dry gas losses is actually based on the flue gas mass of the flue gas, yeah, which is actually mfg multiplied by the heat capacity of the flue gas multiplied by the temperature of flue gas minus T reference, yeah? So this is actually another formula, yeah, that can be actually also used, yeah, to calculate the dry gas losses, yeah, which is the summations of the moles multiplied the heat capacity multiplied by the difference, the temperature difference, yeah, between the exit gas, exit flue gas, and also with the initial temperature or the reference. Okay, so for the moisture losses, yeah, there's actually another formula to calculate it. Yeah, so previously we have the formula of the this, yeah, ml equals to the Cp multiplied by 9H plus W multiplied by the temperature of the flue gas minus temperature of the reference. Yeah. And we can also use this approach. Yeah. So we have this approach here, where the moisture losses can be calculated using the mole of the water multiplied by the heat capacity of the water multiplied by the temperature difference of the exit flue gas and initial temperature, and plus the mole of the water and also the latent heat vaporizations. Okay, so based on these calculations, we can get this, yeah, 0.454 megajoules. Okay. Okay, and then after that, we calculated also the incomplete combustion losses. Yeah, previously also, yeah, there are actually two approaches, yeah, to calculate it, the ICL, ML, and DGL. Yeah. So as I mentioned, DGL, yeah, we have also another formula. We have ML, also we have another approach, yeah, to calculate it, the losses, yeah, and also for the incomplete combustion losses. Previously, it's actually based on the percentage of the CO and also mass of the flue gas, yeah. But we can actually use this approach, yeah, where the incomplete combustion losses can be calculated using this, yeah, the mole of the CO multiplied by the heat of the combustions of the CO2. Okay, so we have the mole of the CO, which is 0.4 moles, yeah. Is it correct? 0.4 moles, yeah, this one, yeah. And the heat of the combustion CO to CO2 is actually 283,000 joule per mole. Okay. Is it given from this? Let me check it first. It's not actually given, yeah, from the problems. Let me have a look first. Wait. Okay, so I think there is actually misinformations in here. Yeah, there should be the heat of the combustions, the delta H of the combustions of the, or we call it the heat combustions of the CO to CO2. Yeah, it must be given actually from the problems. which is actually 283,000 joule per mole. Okay, so yeah, we can get the incomplete combustion losses, yeah, 0.114 megajoule, yeah. And then we calculated the utilized heat, yeah, or the panas yang dimanfaatkan, yeah, or utilized heat can be calculated by heat input divided by minus heat losses, yeah. Then we have this one, 5.37, yeah. So this is actually the heat losses from the DGL, yeah. So from the dry gas losses, from the moisture losses, and from the incomplete combustion losses. Yeah. Then we can calculate the furnace combustion efficiency, yeah, where the utilized heat divided by the input energy, yeah, or the difference between the heat input and heat losses divided by input energy times 100%. Yeah. Then we will have this boiler efficiency or the furnace combustion efficiency. Okay, don't forget again, yeah, be careful to use the similar unit, yeah, to calculate the efficiency. Yeah. And here we set, yeah, the unit of the heat, yeah, it's actually in megajoule, yeah, it's not in kilojoule, it's not in joule, yeah, so please be aware, yeah, be careful in using a unit. Okay, any questions so far until this problem? I know it's actually very, very long. Yeah, so you have to practice. So that's why after this, I will give you exercise, yeah, to do it. Yeah. And yeah, once you do a exercise, I hope that you can actually understand the step-by-step calculations, yeah, especially how we calculate the boiler efficiency. Any questions?
Sir?
Yeah.
Do you mind going to the last page because it is not shown on the PowerPoint?
Oh, really?
Yes, sir. I need to screenshot it, the table.
Which one? Which one?
This one, sir.
Oh, okay, this one. Okay.
Thank you, sir.
Again, yeah, so we have actually approach, yeah, to calculate the losses, yeah. So it's not only use the formula that is actually already explained from Pamiki, yeah. So we have also another approach by utilizing, yeah, the mole of each components and also heat capacity of each components, yeah. It's not, yeah, only using this formula, yeah, while using the mass of the flow gas and also the Cp of the flow gas, yeah. Same with the moisture losses and also the incomplete combustion. Okay, so if there is no questions, I continue. Yeah, so this is the boiler load management. Yeah, so in large chemical plants, always usually use more than one boiler. Yeah, so where every boiler is operated at a load that gives the best efficiency or the highest efficiency. Yeah, and load balancing in chemical plant is one of the programs in energy management. And we have also the rule of thumbs, yeah, how we can actually operating the boilers, yeah. So there are actually 5 rules in here, yeah. So the first one, boiler usually has the highest efficiency in this interval range, yeah, from 65 until 85% of the design capacity. Yeah. And the second one, operating fewer boilers at high load, yeah, is actually much more efficient, yeah, compared with operating more boilers at low load. Yeah. So for example, if we have 2 boilers with the high load capacity compared with the 3 boilers with low load capacity, so 2 boilers with high load capacity will be much more efficient, yeah, compared with the more boilers with low loading. Okay, the third rule of thumbs is operated boilers must be chosen from the most efficient one first. Yeah, so we can actually have calculations of the boiler efficiency, and we choose, yeah, the highest efficiency in the first operations. Yeah, of using a multiple boilers. Okay, the fourth rules is actually large boilers usually has higher efficiency than smaller boilers. So this is actually dependence of the size. Yeah, so larger boilers have higher efficiency. And the best load is fulfilled with boilers with higher efficiency, while the swing load, yeah, or fluctuating load is fulfilled by the boilers with lower efficiency. So this is actually the 5 rule of thumbs, yeah, of using boilers, yeah, in industrial applications. Yeah. Okay, so I have another type of the problems, yeah, in here. So comparing the amount of the boilers with considering the capacity, the design capacity for each boiler, yeah, and we can have a look through the see also the percent or the efficiency of the boiler, yeah. So in here we have a plant which has 3 boilers, yeah. The design capacity is 200,000 and 100,000 pound per hour, yeah, respectively. And we have the average required steam rate is 345,000 pound per hour. Yeah. And we have the real operating pattern is actually given as well in table 3.1. Yeah, so in here. So based on the boiler performance stated in these illustrations, yeah, in this graphic, yeah. So the question is, it is possible to save energy by operating only 2 boilers. Yeah, so we need to compare of using 3 and 2 boilers, yeah, based on the load and also based on the boiler efficiency. Okay, so from the characteristic curve, yeah, illustrated in the left-hand side, so it can be seen that the boiler 2 is the most inefficient. Yeah, so we have in here, yeah, boiler 2 is the most inefficient because we can see it from the steam load, yeah. So and we can actually see also from the capacity, yeah, the capacity of the the capacity of the boiler number 2, yeah. And also from the operating capacity, the boiler 3 may not be needed, yeah. So and also we have the proposed loading pattern without the boiler 3 is actually given in this table. Yeah, so we have the design capacity for each boiler. Yeah, so boiler 1, 2, 3, with the design capacity of the 200,000, 200,000, and 100,000. Okay, and the current operations at the moment, yeah, with using 3 boilers in here. So we have the load of the 140,000. And 140,000 for boiler number 1 and 2, while for the boiler number 3 is only 65,000 pound per hour. Yeah, with the boiler efficiency given in here. So the boiler number 1 is 85%. Yeah. 85%. Boiler number 2 is 77.4%. Yeah, and the boiler number 3 is 76.5%. Okay, so the right-hand side, we have also another suggested operations. Yeah? While we considering only 2 boilers that is actually used, yeah, in this process, yeah, by increasing or adjusting the load, yeah, the capacity load in here, yeah. So we increasing the capacity load of the boiler 1 in 273,000 pound per hour, while for the boiler 2 is 172,000 pound per hour. Yeah, with the desired boiler efficiency at 86% of boiler number 1 and 78% for boiler number 2. Yeah, so we have the total load is actually similar. Yeah, but the only difference is we try to reduce, yeah, the use of the boilers, yeah, and try to increase the load capacity of boiler number 1 and 2, as well as we slightly increase the efficiency of the boiler number 1 and number 2 as well. Okay, so by using calculations, yeah, so we can actually see in here, yeah, so comparing the because the questions is it actually possible to save energy? Yeah, so save energy by operating only 2 boilers. Then we can actually use the fuel consumption calculations, yeah, where we comparing between when we use 3 boilers and comparing with when we use 2 boilers, yeah, with the corresponding boiler efficiency and also the capacity load, yeah, for each boiler. Okay, so the based on the efficiency, yeah, boiler efficiency, we have the formula of the boiler efficiency, yeah. So what is the formula of the boiler efficiency? Let me take a look through the previous chapter. Yeah, so we have efficiency. Yeah, so the boiler efficiency is actually this, yeah, where the M fuel times LHV minus heat loss divided by the M fuel or mass of fuels times LHV. Yeah. Okay, so I write it down here. So M fuels times LHV minus heat losses divided by the M fuels times LHV. Okay, so we can use this formula, but there is actually another way, yeah, to calculate the boiler efficiency. Is actually based on the specific enthalpy of the steam and also the boiler feed water, yeah, or the feed water. Yeah, so we can actually calculate also the boiler, the efficiency of the boiler, yeah, by using that approach. So another formula that can be used is actually this, yeah. So the boiler efficiency will be equals to the mass flow rate of the steam, yeah, multiplied by the heat capacity of the steam. Sorry, specific enthalpy of the steam minus the specific enthalpy of the feed water, yeah, divided by the M fuels times HHP fuels. Okay, so there is actually 2 approach here to calculate the efficiency of the boilers. Yeah, so we can also use this. Okay, so based on the calculations given in the slide, so we know that the H steam is equals to this. Yeah, the specific enthalpy of the steam is 1,350 BTU per pound. Yeah. So BTU per LB for this. So I'll try to write it down here. So H specific enthalpy of the steam is 1,350 BTU per pound. And we have also the specific enthalpy of the feed water equals to 218 BTU. Okay, so we would like to calculate the M fuels, yeah, actually, yeah, the fuel consumptions in here, yeah. But given in here is actually the units is in BTU per hour, yeah. It's not actually the units is not the mass flow rate, yeah, but it's actually the heat flow rate, yeah. So we can assume that this is actually the fuel consumptions, yeah. So by considering also the values of the HHP of the fuels. Okay, then the fuel consumptions, we can get the formula, yeah, which is in the heat flow rate, yeah, equals to the M steam or the mass flow rate of the steams multiplied by the H steam minus H feed water divided by the efficiency of the boiler. Okay, so we can calculate it. Yeah, so for all of the boiler given in here, yeah, boiler 1, boiler 2, boiler 3 with the corresponding load capacity, yeah, for each boiler. Yeah, so we have boiler 1, which is 140,000. Same with the boiler number 2, yeah, for the mass flow rate of this or the loading, yeah, or the capacity loading. So multiply by this, yeah. So the difference between the specific enthalpy of the steam and feed water divided by the boiler efficiency. Yeah. Okay, so we calculated and we get this, yeah, for the current operation pattern when we use 3 boilers, yeah. So we have the total fuel consumptions of this, yeah, 4.86 multiply 10 times 10 to the power 8 BTU per hour. Okay. While when we have 2 boilers, yeah, so with the adjustment of the capacity loading as well as the slightly modifications of the boiler efficiency, yeah, and we can calculate also the fuel consumptions for each boiler, yeah, by using the same formula, and we will get this, yeah, these two for boiler 1 and 2, and the total is actually 4.7733 times 10 to the power 8 BTU per hour. So this is the total fuel consumptions for each operation pattern. Yeah, so the current operation pattern, which use 3 boiler, and suggested operation pattern. And based on these calculations, we can calculate the fuel savings, where there is actually the difference between the total fuel consumptions generated from the current operation pattern minus the suggested operation pattern. Yeah, then we can actually save the fuels around, yeah, this, yeah, 0.0905 times 10 to the power 8 BTU. Okay, any questions until this part? Okay, if there is no questions, then I'll give you exercise. Yeah, so this is for assignment 1 and must be submitted yeah, maybe at 5 p.m. Yeah, so we have around 40 minutes from now. Yeah, so the questions is almost the same. Yeah, with the, if you actually pay attention to my explanations during these courses, yeah, I think we can actually easily work on these questions. Yeah, so the only I just modified the compositions and also the temperature of the entering the initial temperature, also the fuel gas exit temperature, yeah, with the same heat capacity. Yeah, so please you determine the combustion efficiency difference. Yeah? And you can upload it, this assignment, in EduNext. Yeah, I will make the submission folder. Going to EduNext. Oops.